7, 8. I lose track.
I could jersey though.
Who wouldn't?
What's that, Rogers?
No, it says Awesome Fat on the back. It was number 01. Binary. All right. See, I'm just a joke now. I can't even finish breakfast. Left half my hash browns on the plate this morning. Mostly because I was fighting with campus safety. Okay, so let's actually try to get through these slides now since we've... Good strategy, folks. Okay, so we've already spoken a little bit about multiprocessing type stuff, and we kind of mentioned this, what we've been talking about kind of the last half of last class was this idea of the role of memory in our system and how all these different resources are all kind of sharing this one resource that has to be able to let all sorts of different guys use it at the same time, where a lot of the job of our operating system is to manage allocation to resources, and usually it limits one person at a time for at least many situations, okay? So we have all sorts of different kinds of resources, and different resources have different rules associated with them. So in systems where we have, it's called symmetric multiprocessing, where typically you have processors of the exact same speed. So rarely will you see, actually, I don't know if that's ever happened commercially, will you see a dual core machine or a two CPU machine that has different speed processors. They kind of rely on being identical architectures. The processors. And even today, it's most of what we see is multiple core CPUs as opposed to multiple CPU machines. You don't get into the multiple CPU machines until we get into the high-end workstation or server class machines, where we get, for instance, like the Mac Pros have. You can go to a dual core, a dual CPU 6-core machine, which would be 12 physical cores and then 24 logical cores, because each one has the magical hyperthreading, which sort of kind of maybe makes things act like an extra core-ish, kind of. Okay, so but we've been talking about cache, L1, L2, L3 cache. So L1 and L2 live directly on the CPUs, where L3 is going to kind of allow sharing between the individual CPUs. So it's going to sit outside of them on the motherboard, but closer than our actual system RAM will be. But in any case, everything about this is all about sometimes we need to store crap, where can we put it, and how fast do we need to have access to it. That's our, if we were talking about a big picture task that's in the operating system constantly, it's storing stuff, how fast does it have to be, and when will I need it next? Those two kind of go together, I guess. Okay, so then specifically talking about, so this is the dual core thing, so we actually have a single CPU. Each CPU has, we talked about registers a little bit, where they'll be at the top of our pyramid for the fastest memory, right? So these are basically hardware-based variables. And then they have cache on the individual ones, and this is where you'd have that L3 cache out here in modern CPUs. Clustered systems. Most of this is uninteresting, and we're not going to talk about it, but one cool one that is kind of vogue to what we're doing in the world today is this idea of storage area networks. When we think about big hard drives for our home computers, we're probably thinking, 2-3 terabyte drive, something like that. Any of you have like a RAID set up with bigger drives? You have like 2 or 3 terabyte drives strung together to give you 9 terabytes. So there's actually some machines out there that that build hardware-based RAID. So you just basically plug hard drives into them, and they don't even have to be the same size drives, and it just robotically figures out how to, set those up to give you the most capacity with failover. So something we're going to end up talking about in here is this idea of RAIDs. There's a bunch of different RAID setups just at the high level. Some of them have the goal of giving you maximum capacity. But if so if you have 2 drives and they're in a RAID 0, which is just concatenated, so 2 1 terabyte drives will give you effectively a single 2 terabyte drive. But if either one of those drives individually fails, your entire array is gone. You won't be able to access even the stuff that's on one half directly, at least. Then you have RAID 1, which is actually a mirroring type thing. So that guy's goal is 100% duplicating data. So whenever you write something to one drive, it also gets written to the other drive. So at any point in time, if you have one drive that fails, the other one is identical and you haven't had any downtime. You'll get a notification that a drive has failed, so you'll have to swap it out. But your machine will keep running, so you just go and order this part again, pop it in, and the machine will automatically copy everything over, so they're back to where they were. So it'll rebuild it, And then as you get up to the higher RAID levels, they become more expensive, typically to set up, but they also give you kind of that hybrid where you get additional capacity while also having failover. And in big, really important systems, you can have arrays set up where you have you could have up to 3 hard drives, 3 physical drives fail at once and still not lose data because of how the failover works and how it rebuilds and stuff like that. So that's what RAID setups are. But now we have this kind of another level that kind of goes above that called a storage area network, or SANs, where it's a collection of hard drives, essentially, instead of computers. And the idea is this gives you cloud storage. So storage area networks are really our starting point for cloud storage, where we can have zillions of terabytes storable in Google's cloud or Amazon's cloud or something like that, when we all know that we're all pretty sure that nobody's making a special zillion terabyte hard drive for Google, right? At the very least, we know that we can't go and buy them at Best Buy, but we can at least be pretty sure that Google's not getting drives that are really any bigger than consumers can get. So your maximum drive size out there today is about 3 terabytes. I think there might be a company that makes a 3.5 or a 4, but let's just say 3 is kind of our and the same thing is going to be true. Those are the same parts that Google is buying. They're just setting them up in storage area networks to allow a whole bunch of those guys to work together and have failover to handle data loss and stuff like that. Okay. So this is kind of that idea here, where you have a central hub where all your data lives, and behind this you might have a whole bunch of hard drives that are connected somehow. Okay, so multi-programming operating system, this kind of comes down to, it's maybe the predecessor to true multitasking. So multi-programming would indicate that the computer is capable of handling more than one program running on the machine at once. That is different than what we typically call multitasking, because multitasking is really the act of the human being being able to interface with the operating system and switch between applications. So we care very little about how it's actually implemented under the hood, as long as we believe that 2 applications are running at the same time. Right? The reality is, in older computers that had just single core processors, we would be in a situation where only one thing can actually happen at once in a single core processor. So the job of that CPU was to go really, 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 really fast, to just bounce back and forth, back and forth, back and forth between 2 tasks to convince us that both were happening at the same time. Make sense? So difference between multi-programming, which is going to be more of the under-the-hood operating system level, and multitasking, which is going to be more the human perception of what's going on. All right, so the whole purpose of multi-programming was really need for efficiency. We have the CPU that's sitting there that's capable of doing a lot of stuff, and the human being is using their programs. Even if they're a heavy user, a human being is going to have an impossible task of keeping the CPU busy 100% of the time. So we might as well have this resource, the CPU, being able to do other things, operating system related. Even predating the idea of having 2 different user programs running at once, there's other things on the operating system that kind of need to be there, checking on different resources, releasing resources, cleaning up memory, things that are happening under the hood that we're happy that it's happening. We don't need to know about it happening, but would be beneficial if the CPU can work on those things as well. And then this kind of leads us into one of our modern jobs of the operating system, which is job scheduling. That is staging applications to run on the CPU so that the CPU convinces the user that they're getting 100% of the time, but other crap still gets done. Okay, so that's job scheduling. So we have CPU scheduling, which is going to be the handling the resource that is our CPU. And then we have job scheduling, that is good, or process scheduling, you can think of it like that, which is the job of handling the resource that is our collection of programs that are currently running on the computer that would like to get some CPU time. So dealing with those two things together is what actually makes programs get processor time. Okay? And then we talked a little bit about interrupts before, where whenever there's I/O, we want to keep our CPU busy, so we're going to toss that to somebody else to deal with the I/O stuff, and then they can get back in line for the CPU. So then we get down to time sharing, or they just call it multitasking, although there's a couple of different approaches to multitasking that we'll talk about later. But the idea of this is, let's say you have 3 or 4 programs as an individual user. You have Microsoft Word open, you have your web browser open, you have your email client open, and Slack or something. And you want all of those to feel like they're all working at the same time. So behind the scenes, there has to be some sort of way, and the best way to view this is if you have a single core processor, right? Modernly, the problem gets easier for us to wrap our mind around because our dual and quad core processors can do 2 or 4 things simultaneously. But from a programming perspective, it becomes more difficult because you need to make sure that the 2 things that are happening at the same time don't conflict with each other. We can't add this number to this number until this number has been figured out. Okay, so we can't have those 2 things happen at the same time. So the programming side of things does get more complex. But from a time-sharing multitasking perspective, it's easiest to explain on a single core processor example, where if you have 4 applications all vying for the same single resource, because CPUs are so fast, the best way to pull it off is to give one of your applications some number of microseconds, another one some number of microseconds, another one some number of microseconds, another one some number of microseconds, then keep doing that over and over and over again. And from our perspective, it's almost like a movie, where we know movies are presented in 1 frame at a time, okay? But the frames are happening on the screen fast enough that we don't visually see that there's any sort of delay. Make sense? So computers are even faster than that. So as long as they can fake us into thinking that everything's getting CPU time, we're none the wiser, and that's cool. All right, so that's the idea of multitasking as opposed to multiprogramming. That would make a reasonable quiz question at some point. What's the difference between multiprogramming and multitasking?
So what exactly is the difference? The multitasking is the human perception of what's going on, but the multiprogramming is just capability to handle more than 1 program on the machine at the same time?
I think it's a fair answer. Okay. So this is kind of an introduction to, again, what does it take? So everything kind of becomes this big conglomerate of how an operating system needs to operate, where all the pieces work together. So we've already talked about, we have the CPU scheduler, we have the processor, the job scheduler. Now we have to think about memory management, because this one resource, the memory that everything in our computer is having to work with at some capacity, also is going to be housing aspects of each of those programs or each of those jobs that want to get CPU time. And once they get CPU time, the CPU is going to be trying to get stuff from memory. So how do we actually organize memory in such a way that our CPU can efficiently get stuff related to the programs that are in memory? Understanding that we have a finite amount of memory, right? We might think we have, a big amount of memory in our computers today, 4 gigabytes, 8 gigabytes, whatever, but it's still a finite amount of memory. And even though we have a finite number of programs that are running on our machine at once, would you be surprised to know that there's 30 programs running at once on your computer?
With this memory, we're talking about RAM, right?
RAM, yep. I mean, that wouldn't surprise you, right? I mean, between the applications that we have open, so if we just look at the applications I have open on here, okay, so between all those and all the extra stuff that's running at the operating system level, we can be convinced that there's a lot of crap running on the computer at once, right? And each one of those guys is getting some CPU time. Each one of those guys is having to store some of its stuff in memory because that's where we house the parts of the program that's going to run next. So even if a single program only gets a small little piece of memory, we have to have enough of it in memory so that the next time it gets CPU time, it can feed off of what's currently in memory. Because if we don't have enough of it in memory, then it has to go to something called virtual memory, which is really, really slow memory. That's us using our hard drive for fake memory. We do something called swapping, where we bring in slow stuff that should be in memory into actual memory, and then we can bring it to the CPU. So there's this whole war that's happening where all these parts need to work together to give us an operating system that's fairly well balanced. Okay? So this is where machines start feeling sluggish. As we look at how machines keep evolving. Let's look at the newer operating systems that have come out. So iOS 9 for the iPhone just dropped yesterday, day before, I guess. Any of you who's running iOS 9? The folks in here. Okay, well, other class has somebody running it on a 4S. So probably feels a little sluggish on the 4S. All right, so if we were going to sit there and compare how it's running on his 4S to how it's running on my 6 Plus, it's going to run faster on mine. Mine's many, many years newer than his, than his phone is. So that's a piece of hardware that doesn't suck. It's still, reasonable piece of hardware, but it's running a very modern operating system that wasn't necessarily designed with just that hardware in mind. It was designed with newer stuff in mind. So you have a situation where that operating system is maybe making some decisions based on how long a single job should get CPU time, how much stuff from each job should get stored in memory, things like that. Trying to tune those thresholds to make all your applications feel like they're all really fast. And it's probably making some decisions that are passable on the 4S, but really are probably a little bit too aggressive for the 4S in terms of what it can keep up with. So it feels sluggish because it's spending more time than was intended bringing certain things into system memory, moving things between the CPU and I/O, that kind of stuff, doing operating system-y stuff. All right, so that's an important thing to understand when we try to evaluate new operating systems that come out. Is you can't just blanketly say this operating system is bad because it's slow. Now, if you have the newest, latest, greatest hardware and it's slow on there, okay, now we got to start talking about whether they've made some poor decisions in that operating system are more likely in today's age. There's a horrible bug that's taking up 90% of your CPU time behind the scenes, so your applications are only vying for 10% of it, and your battery life just takes a dive, right? That's probably what we'll see, because if your CPU is sitting there burning 90% of the time, because a couple slides ago we mentioned that a human being finds it difficult to keep the CPU busy 100% of the time. Fair enough, we can believe that in a heartbeat, right? But the reality is, well, let's take the flip side of that coin and say one of the goals of an operating system, specifically the CPU manager, would be to keep the CPU busy 100% of the time. That would be one of its goals. What percent of the time do you think, in practice, CPUs are busy? Maybe mentioned in here already, but let's see if you retained it. Goal is 100% of the time. In practice, what do you think the amount of time a CPU typically stays busy? 12 to 15% of the time? 23? 1? So he said 1? He's the closest. Yeah, somewhere between 1 and 5% is probably the reality. So our CPU sits idle 95, 96, 97% of the time. On average.
Not bad.
Well, if the goal is 100%, if you come in to take an exam and your goal is to get 100% of the exam and you get a 3%, How do you feel?
But are you preserving the longevity of it by not using it? Or?
Well, possibly. CPUs don't have moving parts, so that you probably don't really have CPUs that wear out. When CPUs go bad, it's typically because the heatsink or fan failed and it burned up. Or the sensor on the motherboard that detects heat didn't do its job and shut it off, that kind of stuff. You typically don't have CPUs that, unless it was a manufacturing problem, that wear out. Okay? But, I mean, the point is it is different. If you came in and hoped to get 100% on an exam and got a 3%, you'd be upset. Okay, because there's a far cry, right? There's a far cry between that goal and what you accomplished. Now, the reality is, though, in computing, if the operating system has the goal of keeping it busy as close to 100% of the time as it can only make decisions given the jobs that it's given. Okay, and as our CPUs get faster and faster and faster and able to accomplish tasks even more quickly, and the way we use our computers doesn't necessarily evolve at the same pace. You know, the way you use a computer today isn't substantially different than the way you used it 2 years ago or 4 years ago. You still have multiple applications open. You're still checking your email, browsing the web, things like that, right? So it's not substantially different. So the reality is as our computers get faster, they're going to spend less time doing the stuff they did last year. With the last year's model CPU. So just because it's only busy 3 or 4% of the time doesn't mean it's not accomplishing its task very, very well. It just means that you haven't given it enough work. Okay? And we've already said that a human being can't give it 100% of the work. I mean, we're not fast enough. Okay? The reality is our CPUs are really, 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 really fast. Okay? And this actually relates to something we see all the time for those of you who build computers. It's human nature, typically, to try to get the fastest CPU, right? You look up there and says, well, I can get the 2.4 gigahertz, or I can get the 3.2 gigahertz. Oh, yeah. Way better. Way better, right? The reality is from a consumer perspective, you may notice zero difference between those two, except when you look at your bank account. All right? So typically, the best place to spend money first on either upgrading a computer or building a new computer is typically hard drive first, fast hard drive. Secondarily, memory. You want to have enough memory. Speed of memory is only going to give you negligible performance differences. You know, when you build your gaming rigs, you can get the 8 gigabytes of generic brand X made in some foreign city by 6-year-olds or something like that, RAM. Or you can get the Corsair gaming RAM that has really cool colored heat sinks on the outside of it and just looks dangerous, right? At twice the price. I guarantee you even the most effective gamer will not be able to tell the difference between those two unless they knew it was in there. Okay? They wouldn't be able to say, if you put 2 machines in front of them, one with each one, they would just be literally doing a 50-50 guess as to which one was faster if the machines were identical otherwise. We were talking such millisecond differences that from a human being's perspective, it's going to be imperceptible to us. Okay? Now, from a gamer's perspective, though, just kind of flipping this around, the same thing goes with our video cards today. Just to kind of put this in, finish that conversation about gaming machines. It's also human nature for us to go out and buy the latest, greatest, coolest graphics card, right? Okay, so if you had unlimited funds, right? Obviously, we have to be good stewards and okay, well, it's $10,000. I don't have $10,000. Yeah, I want it, but I ain't getting it. Is the punchline there, right? So, but if we had the money to do it, we would get the best, right? Well, so let's say I gave you the latest, greatest $800 graphics card, and I gave you the latest, greatest $200 graphics card, more of our budget pleaser, entry-level gaming graphics card. Would you be able to tell the difference?
Probably.
In many, many, many situations, you would not. because your $200 graphics card can probably support 60 frames a second pretty easily at high definition resolution under normal circumstances. Okay, his $800 graphics card going to be able to support 240 frames a second under normal circumstances, no harm, no foul. Issue here is that the human eye can only see about 30 frames a second. Okay? Human eye can only see about 30 frames a second. So why do we need 230 frames a second if yours can do 60, which is more than I can see? Did you just waste your money? You did? Throw it away? Okay. When you're gaming on that $200 card, most of the time you're fine. When are you not fine?
When you're in a really busy part of the game.
You get into a really, really busy part of the game, and your frame rate drops to 12. Okay? Your frame rate drops to 111. Okay? Still way, way, way clear of what the human eye can detect. Right? Okay? But still, now we have choppiness on the screen from you, and everything looks crystal clear to you. Okay? Even though your card is operating at a fraction of what it's capable of. Half of what it's capable of, right? Okay, so that's the reason to pay for the more expensive card. Not for the average case, but the worst case. You can just dive into the busiest part of the game and have all the graphics turned all the way up, where all the explosions and particle effects and all this stuff, and you push the latest, coolest card to its limits, and you drop down to about 80 frames a second. Just awesome, right? So, in any case, there's kind of a pecking order for where we spend our money. Our decisions become a little bit different when we're talking about gaming machines, because we are having to take into consideration what games we're going to play and what is the worst case going to be. You're going to spend substantially more time at around 100% CPU usage when you're playing a video game than you will when you are doing normal operating system type tasks. This becomes even a little bit further on the other end of the spectrum when we, your CPU actually has more free time when we play our games today than it ever did before, because now it can push off large percentages of the stuff it used to have to do onto our GPUs. So anytime it has to do a whole bunch of floating point math or something like that, we'll throw it to the GPU. Okay, but punchline of all this stuff, it's all about resource allocation and how they get managed for doing their stuff. Somebody needs to make that decision. The process scheduler, the CPU scheduler, is going to have to make this decision of, oh, here's this task that needs to be accomplished. Do I give that to my general purpose CPUs, or do I throw that to my GPUs? Okay, so yeah, we just added performance by adding more resources, but to manage more resources now becomes a more difficult problem. Okay, make sense? Chicken or the egg type of situation. So that's our job as operating system designers.
I don't know if it's related, but do you know what the limitation is where only iPad Air 2 and newer can support the split screen for iOS 9?
I'm sure it's a CPU thing. Yeah, I'm sure it's very related to what we're talking about. That it didn't meet that threshold for performance. There's not an operating system reason, but they probably tried to launch 2 applications on it, and this isn't working well. They both are sluggish to the point of not really being usable, would be my guess. Because it doesn't work on because I have the first generation Air, so yeah, so we don't have it. Second generation Air has it. Newest generation Mini has it, which is second generation Air components with the smaller screen size, and then the Pro will have it. So completely related to what we're talking about. All right, out of time. What do we got left to do? Well, whatever. I'll see you next week. All right. But we could sing happy birthday to Katie.
Sorry, you guys don't have to.
Really?
I mean, if you really want to.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Katie. Happy birthday to you. Got it on recording.